I am going to, as Greg said, announce the SSERVI Angioletta Coradini Mid-Career Award. It is given annually to mid-career scientists for broad, lasting accomplishments related to SSERVI fields of interest. Angioletta Coradini was an Italian planetary scientist who has inspired astronomers around the world. And this year, I'm very pleased to announce that Dr. Timothy Glotch from Stony Brook University has been given this award. So thank you to Tim for all your work. I'm going to say a little bit more about you and then hand it over. Dr. Glotch is the professor of geosciences and associate dean for operations and facilities for the College of Arts and Sciences at Stony Brook University. He received his BA in astrogeophysics from Colgate University and his PhD in geological sciences from Arizona State University. He is a co-investigator for the Lunar Reconnaissance Orbiter, Diviner Lunar Radiometer and Instrument, and participating scientist on the OSIRIS-REx asteroid sample return mission. He combines terrestrial analog fieldwork, infrared remote sensing, and laboratory spectroscopy to better understand the composition of the crusts of the moon, Mars, and small bodies. In addition to all that, Dr. Glotch has been a principal investigator for 2 SSERVI teams and has led an effort of over 50 researchers and students in using state-of-the-art laboratory theory and field techniques to further NASA's science and human exploration goals. He exemplifies the teachers, scholars through the integration of outstanding research and education. Even mid-career, he has already received numerous NASA Group Achievements Awards for his various missions, as well as the National Science Foundation's prestigious Faculty Early Career Development Program Award. He has authored or co-authored more than 40 publications and has served as associate editor for the JGR Planets. So I think you can all agree with me, he's most deserving of this year's Angioletta Coradini Mid-Career Award. And I'd like to once again congratulate Tim and welcome him to share some thoughts.
Thank you, Christina, very much. I appreciate it. Thank you, Christina, for that introduction. I really appreciate it. I'm really honored to receive this award. And it's especially gratifying to receive an award named after Angioletta Coradini, who's a gifted and really influential infrared planetary spectroscopist. As many of you know, infrared spectroscopy is a topic that's near and dear to my heart. It's comprised the better part of my career. So that's wonderful for me. I'm also really grateful to be in the company of the past award winners, Dr. Barbara Cohen, Dr. Jennifer Heldman, and Dr. Harold Hiesinger, who are all scientists that I respect and admire a great deal. I want to start with some important thank yous. So first, my nominators, Dr. Kelsey Young, Dr. Scott McLennan, and Dr. Dyer. I'm really grateful for their guidance and belief in me over the years. I'd also like to thank the LRO spacecraft, or I guess, the scientists and engineers that have made it the cornerstone of the renaissance of lunar science in the last decade and have kept it going. LRO, and specifically the Diviner Lunar Radiometer experiment, completely changed the path of my career. And so thanks to Dave Page, the Diviner PI, for his continued support of me and my students over the last decade or so. Thanks also to SSERVI, which has been responsible for another major change in my career path. I think the RISE and RISE-2 teams, we've been able to contribute a lot towards NASA science and exploration goals for the moon and other airless bodies. And SSERVI has really made possible a lot of high risk, high reward science for me and students and co-Is on the team that otherwise might have had a hard time getting funded. So I'm really grateful, Greg, Christina, the rest of SSERVI Central for your support, as well as the support of previous director Von Pendleton and associate director Brad Bailey. And then finally, I want to thank my family, especially my wife, colleague, and scientific collaborator, Deanne Rogers. Her support and encouragement since the time we were grad students has been instrumental in whatever success I've had. So leading up to today, I've had a lot of privilege and help to get to where I am. I grew up in a really solid middle-class family with loving parents who encouraged all of my interests and were able to save enough to send me to a really good private university with minimal debt. At Colgate, I was able to interact with faculty who loved to teach, were my first research mentors. And through there, I was also able to secure outside researcherships with Bill Botke and Jim Bell, who many of you know. They both taught me a lot and would go on to advocate for me later in my career. But it's not lost on me that if my personal circumstances had been even a little bit different, that all those opportunities might not have been available to me. I want to focus just for a few minutes, though, on the wonderful fortune I had to work with three mentors who were incredibly important in my journey as a scientist, professor, and as a leader. My PhD advisor at ASU is Phil Christensen, seen here with me at the launch of the 2001 Mars Odyssey spacecraft. And look at all that hair I had. Good. Phil provided me a basic foundation in remote sensing and planetary science and gave me my first opportunities as a grad student to work on missions, sometimes being the first person to analyze new data, coming down from one of his infrared instruments he sent to Mars. And I can't describe what a thrill that type of opportunity is. He also gave me the freedom and encouragement to pursue my own ideas and taught me that better is often the enemy of good enough. And that's a mantra my own students often hear me repeat sometimes. After ASU, I worked with George Rossman, my postdoctoral advisor. He's as brilliant a mineral spectroscopist as there is. He's also one of the kindest people I've had the pleasure of knowing. And working with him gave me the skills and confidence I would need to start my own lab one day. So I do remember, though, being intimidated on my first day when I walked into his office. And for fun, he gave me the mineralogy final exam that he had just given his students while he sat and watched from across his desk. I think I got a C+, but apparently that was good enough because we immediately proceeded across the hall to his lab where he handed me a screwdriver and had me assist his lab tech, Liz Miura, in fixing his micro FTIR. So on day one with George, I learned the valuable lesson that you can't be afraid of your own equipment. And finally, there's Darby Dyer. Incredibly, I couldn't find a photo of us together, so you get this Photoshop tack job. I started collaborating with Darby early in my career at Stony Brook, and she immediately impressed upon me the value of careful laboratory mineralogical analyses, and importantly, making those results easily accessible to researchers worldwide. By the time I'm no longer a mid-career scientist, I hope I'll be known as Darby as someone who's willing to do the dirty work of fundamental mineral spectroscopic measurements that benefit the Earth and planetary research communities. And I'll close this slide by saying that I've been extremely lucky to have Darby as the deputy PI for both the RISE and RISE2 SSERVI teams. She's collaboration personified, and I've learned so much from her about teamwork, leadership, and how to make your text fit into limited proposal or paper space. So I encourage you, seriously, after this session, go read one or two of her papers because they're like poetry. It's crazy. Okay, so I think it's kind of become a tradition at these types of talks to offer unsolicited advice to members of the community. So I'm not going to pass up on that chance, but I'll keep it brief. And here it is. Say yes more than you say no. I've benefited a lot from saying yes in my career, and it's helped me to get to where I am now. And I mean this, though, in a lot of different ways. So say yes to collaborative efforts within your subdisciplines, but especially if your expertise can contribute to a cross-disciplinary team. This is where a lot of the fun and exciting science gets done. Say yes to paper and panel reviews. I learned so much from these, especially early in my career. And if you haven't been offered the opportunity, find the right editor, program manager, and volunteer. And there are probably editors and program managers who might be listening right now who I've said no to even recently, but just notice that this says say yes more than you say no, not always say yes. Say yes to public outreach and engagement. You could potentially find yourself on a children's TV game show with a caption under your name that appears to question your very professional identity. But most of the time, you'll be bringing the joy and fascination of our profession to members of the public, inspiring the next generation of scientists and explorers. I'll also say that if you, like me, are a cishet white male, it's especially important to say yes to responsibilities that are traditionally foisted upon women and people of color. This might include, but it's definitely not limited to, certain types of committee assignments, or leadership positions, university and community service activities, and especially EDIA work. If you're wondering how you can get started with some of this, try the SSERVI EDI focus group that's led wonderfully by Jay Greer. You can sign up at this website there. And I can say with confidence that erring on the side of generosity with my time for these types of efforts has never hurt. I'll close here by saying that I get that people have to protect their valuable time, and we shouldn't really glorify overwork or long hours in the lab. I've reached a point in my career where I have a reasonable semblance of work-life balance with lots of time for my family, which I'm really grateful for. At the same time, there have been plenty of points in my career where I've had to sacrifice personal time to focus on professional efforts that are also important to me. So I'm sure there will be more of those, and I'll continue to say yes to them if I think they'll benefit me and my research group or my community. Okay, I'd like to use the rest of my time to talk about science and the incredible role that students and postdocs working with me have played in my own scientific development and in furthering the science that I'm personally interested in. And I'll focus here on work related to fundamental spectroscopy, airless bodies, and samples. But if any of my Mars-focused current or former students are listening, I love you guys too. I'm really proud of the work my students have done to develop tools and methods to calculate infrared optical constants over a wide wavelength range. Eli Skloot, who's now at PSI, has put together a HAPI code that uses visible near infrared measurements of minerals at lots of different phase angles and different grain sizes to calculate robust visible near infrared optical constants. You can try the code here for yourself if you'd like. 3 other former students, Jessica Arnold, Chung Ye, and Melinda Rux, greatly advanced the state of the art for modeling mid-infrared optical constants from oriented single crystals, which is the best way to do it. These include some of the first studies of geologically important minerals with monoclinic or triclinic symmetry, for which both the measurements and the modeling is complicated. I hope to expand upon this in coming years. Eli's recently received funding to do more optical constant work, and I'm working with her on that. And I'm actually going to be looking for a postdoc to help with this. And so if you know someone or you might be that person to help me out, let me know. Give me a call. Send me an email. The whole point of all of that effort we've put into developing methods for calculating optical constants over the last decade or so has been to enable more quantitative analyses of remote sensing data through the application of radiative transfer theory. Jesse Arnold started our work combining T-matrix light scattering methodologies with HAPI theory and other types of radiative transfer models. And Gen Ito, who's now a postdoc in France, picked up that work, 2 papers that demonstrated the application and also improved upon it by including a correction for densely packed regolith. Like, that's more realistic. That's kind of been an Achilles heel for HAPI, over the years. Earlier this week, you might have seen a talk by Vanessa Lowry, who's a grad student at University of Central Florida, where she used these methods to show that you can explain the infrared spectra of Trojan asteroids without the need for extremely low packing densities or transparent salt matrix, which are a couple ideas that have been floating around the literature for a little while. And it's been really gratifying to me to see others pick up and use these types of techniques for their own applications. Through our work and the work of many others on the Diviner team, including Ben Greenhagen, Carrie Dawson-Hanna, Ian Thomas, and Neil Bowles, we've come to understand that if we want to compare laboratory infrared emission measurements to actual thermal emission measurements of airless bodies, we need to do so in an appropriate environmental chamber. Catherine Shirley made a really tremendous contribution to our ability to do this with a systematic laboratory study of the effects of particle size on infrared spectra in a simulated lunar environment. And she saw trends that are nearly the opposite of what we see under ambient conditions. So I think these types of data, these fundamental data, will be crucial for further analyses of Diviner data, as well as data from Lunar Trailblazer, and hopefully a hyperspectral mid-IR imager, which absolutely needs to be sent to the moon. I'll also note that a current grad student, Laura Breitenfeld, who I'm co-advising with Deanne Rogers, has used similar simulated asteroid environment spectra to build a training set for a machine learning model to quantitatively analyze OSIRIS-REx Otis data. So I think the successful demonstration of that technique will pave the way for similar models to be built for hyperspectral mid-IR data sets for airless bodies throughout the solar system. system. That's something I'm really looking forward to and excited about. I've also made some advances in Raman analyses of Earth and planetary materials. My former postdoc, Mehmet Yeseltas, now professor at Kırklareli University in Turkey, working with two former students, Stephen Jarrett and Jordan Young, show that you can use confocal micro Raman instruments and measurements to understand relationships of minerals and organics in 3 dimensions at submicron spatial scales. These are just a couple examples here for class 2 shock basalt from Lunar Crater and an ordinary chondrite meteorite. I think the perfection and application of this technique will be incredibly useful as we've entered the age of returned sample analyses. Trying to move on. Just got 2 slides left. A few years ago, I had a group of students, Stephen Jarrett, Melinda Rux, and Melissa Sims, who have all been interested in impacts and high pressure processes. And if you know me, this is not my scientific wheelhouse at all, but I was lucky enough to co-advise them with other faculty and scientists at Stony Brook and at Brookhaven National Lab. But their mutual interests led to some great collaborations and novel sample analyses and experiments. Melissa, who's now a postdoc at Johns Hopkins, uses synchrotron, X-ray techniques, and Raman spectroscopy to understand impact shock in minerals. She conducted a series of novel rapid compression experiments and analyzed samples in situ using X-ray diffraction. Her work showed that amorphization in plagioclase progresses over a really wide pressure range rather than instantaneously, suggesting that amorphization can be heterogeneous. These experiments support the idea that amorphization pressures for plagioclase occur at lower pressures than are typically thought of. This has really big implications for our understanding of the pressure and temperature conditions experienced by rocks during meteor impact. Melinda was approaching kind of a similar set of questions from a very different angle. She's fascinated by analyses in the literature of the shock-induced high calcium mineral tisentite in extraterrestrial samples. And so she set about to synthesize it in order to better understand its formation conditions and its potential to place constraints on shock pressures and temperatures. Her experiments used a really novel spike heating protocol that could reach impact relevant temperatures within about a second and approximate the time temperature conditions in a post-shock melt. And her work established that heating for impact relevant timescales isn't really sufficient to completely transform plagioclase to this mineral tisentite. And so it instead forms from an amorphous plagioclase during decompression. So I want to end with some recent and I hope future work that I'm really excited about. I spent the last 5 years or so working with students and postdocs to try to better understand the capabilities of near-field infrared spectroscopy and imaging, or nano-IR techniques for analyses of Earth and planetary materials. We've certainly not been pioneers here, but we've recognized the potential of nano-IR to start addressing a whole different set of questions compared to standard laboratory infrared or remote sensing infrared techniques. Here, former postdoc Mehmet Yeseltas has, I think, emerged as a world leader in the application of this technique to carbonaceous chondrite and ordinary chondrite samples. At Stony Brook, Jordan Young, who just graduated, used nano-IR measurements to collect multispectral images and full spectra of this CM2 chondrite in preparation for analyses of eventual returned SARS-Rex samples. In the coming months, I'm really excited that we'll be bringing online a new instrument at Stony Brook that will enable us to do hyperspectral imaging of samples at 20 nanometer spatial scales. And SSERVI has been instrumental in the successful proposal and acquisition of that instrument. So this will, I hope, enable a new frontier in mineralogical analyses and organic analyses of meteorites, Apollo samples, and return samples. So I'll end here, again, with gratitude for everyone I mentioned, and also noting that there's so much great science I couldn't talk about, and that the young scientists I've mentioned have done, and I'm really grateful to have been a part of it. So thank you very much.
Thank you. Thank you very much. That was really nice to hear a little bit about your background as well as the research. And again, you're still putting your students forward. So thank you for that as well. Were you all able to hear me? I just had to unmute myself. Okay. I don't know what Zoom was asking me, but with that, I will congratulate Tim again and hand it back to Greg. So thanks, Tim.
Great. Tim, thank you so much for another inspiring talk. And I want to let people know, Tim alluded to this, but how much we're all familiar with his scientific contributions, which are profound. But he has been a very active leader in equity, diversity, and inclusion efforts. And Tim, I really want to thank you for that. There's nothing more important that we're doing, and your contributions have been profound in that as well. So thank you.